Hey friends, welcome. Today we will be discussing one of the topics from statistical thermodynamics, and that is very famous Boltzmann distribution law, or it is also known as the Maxwell Boltzmann distribution law. This is also popularly known as the most probable distribution also, and basically this statistics was given before the advancements of the quantum mechanics. So this is also known as classical statistics also. And the particles generally, all the classical particles will be classified under Maxwell Boltzmann distribution statistics, and these particles they are famously known as either Boltzmann-ons as well as Maxwell-ons. So over here, in order to start the derivation of, suppose we are considering we have n number of identical and distinguishable particles at a particular temperature T, and energy of the system is E. For this derivation purpose, we are considering that we have a closed system wherein the number of particles as well as the energy of the system as well as the temperature of the system will remain constant, and the number of particles, energy and the total energy will remain constant. Also, whenever we are discussing a statistical thermodynamics, generally we are considering the gaseous system and the system are always under equilibrium. Okay, so these particles will have certain characteristics. That is, first characteristic is that the particles they do not attract or repel each other. That is, particles will pass by each other without any influence on each other. The second characteristic is that the particles are distinguishable. Suppose if we are considering say any particular gas, then in any particular gas, say suppose if we are considering I am taking hydrogen gas or I am taking oxygen gas, then in this gas, suppose if we have say n number of particles, then n number of particles will, all the oxygen molecules will be distinguishable. I could distinguish each particle, and when they will change the energy state, this will result into a new macro state. Then the third characteristic is that there is no restriction assigning the energy levels to the particles. So this is the third characteristic, and there is no restriction on assigning the energy level to the particles, and that means we can assign any energy level to the particle, and suppose we have n number of particles, so they may be distributed in different energy level. Also, all the particles could be in one energy level also. So these are the three characteristics of the particles that are under the consideration. Now let us consider the distribution of these particles amongst different energy levels. So we have total energy E, and this energy is distributed amongst different energy levels such that energy level E1, energy level E2, energy level E3, and up to we have energy level EI. Okay. Now amongst these energy levels, the particles are distributed in this energy level such that we have n1 amount of particles in energy level E1, we have n2 amount of particles in energy level E2, n3 amount of particles in energy level E3, and we will have ni amount of particles in energy level EI. Okay, so this is how the particles are distributed amongst different energy levels such that, so the total n, suppose we have n number of particles, so total number of particles will be equal to n1 plus n2 plus n3 plus up to ni, and that will be equal to summation ni, and that is equal to n. And similarly the total energy will be equal to, so n1 number of particles in E1 energy, so we will be multiply both this will give us the total amount of energy in E1, total amount of energy in E2, total amount of energy in E3. So we will have n1 E1 plus n2 E2 up to NiEi, and that will be equal to summation NiEi. So this will give us the total amount of energy. We are finding out the Maxwell Boltzmann distribution. So the final expression that we will be getting will give us the distribution of these particles amongst different energy level. Okay, so this is the distribution, and for such a distribution, the thermodynamic probability, or we can say that the number of ways in which n number of particles could be distributed in EI amount of energy, could be given by the thermodynamic probability. And the thermodynamic probability in different books, it is represented by different ways. In some books it is represented by P, in some books it is represented by uh, W, in some books it is represented by omega. So we will be using thermodynamic probability W, and thermodynamic probability, it is defined as, for a particular macro state, the number of possible microstates corresponding to that macro state is the thermodynamic probability. So suppose we are considering that this is our distribution, and for this particular distribution, the thermodynamic probability W, it is written as W is equal to total number of particles n factorial divided by the distribution of particles. Say suppose we have n1 number of particles plus n2 factorial plus n3 factorial dot dot dot, and we will have I factorial. Okay, so this is how we are representing the thermodynamic probability. Now we will be solving this expression in order to get the most probable distribution, because this expression, it represents the distribution. So we will take a logarithm on both hand sides. So we will have ln of W will be equal to ln of n factorial. Now over here oral multiplication, so ln of n is the ln of n will be our addition function, because we know that ln of multiplication is an addition function. Also this is in division, so we will have minus sign, so minus ln of we will have we could write it in this way, ln of n1 factorial plus ln of n2 factorial plus ln of n3 factorial plus dot 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 ln of ni factorial. And this addition we could write it as, we will have ln of n factorial minus summation ln of ni factorial. Okay, over here n are the number of particles which represents any particular gaseous system, and we know that for 1 mole of any particular gaseous system, it is 6.023 into 10 raised to 23 molecules, which are very large number. And whenever we are taking very large number for this type of factorial, we could apply Stirling's approximation or Stirling's formula or Stirling's approximation to solve such type of factorial. And Stirling's approximation, basically it could be applied for very large number, and over here we will have very large number. So Stirling's approximation, it says that ln of x factorial, it could be given as x ln x minus x. So this is our Stirling's approximation. So this Stirling's approximation we will be applying to both the ln, that is ln n factorial, and summation ln of n I factorial. We will have n ln n minus n minus summation of ni ln ni, and we have minus and this minus, so this will be plus summation of ni. Okay, and also we know that this summation of ni is equal to n, that represents the total number of particles. So this n and this n will be cancelled out, and we are left with n ln n minus summation ni ln ni. So this is our expression. Under most probable distribution, the value of the thermodynamic probability will be maximum, and that will be a unique value or a single valued function, or the value of thermodynamic probability will be a constant. Okay, because when the system is under equilibrium, the system is under most probable distribution, and when the system is under most probable distribution, suppose these are the distribution of particles, so under most probable distribution the value of thermodynamic probability is maximum as compared to all the other states. Okay, so this will be or the value of thermodynamic probability will be a constant value, it will be a single value, and it will be a maximum value. Okay, so also this could be explained by taking the example, that is, suppose we are standing or we are in a room, and in that particular room if we burn an instant stick on one corner, and if you are standing on another corner, then what will happen, that is, the smell will come to you and the intensity will increase. So this intensity will increase up to a certain time when, or up to when the system or when the whole of the room will be saturated or will be under equilibrium, and after that the amount of the smell that you are getting will not increase. So at that particular moment, what is happened is that the system is under the most probable distribution, and the system is the most stable system, and under that particular state the distribution of particle has obtained a maxima. Okay, so under most probable distribution, the value of thermodynamic probability will be a single valued, and that will be a maximum value, and that will always be a constant. Okay, so when we differentiate this equation, when we differentiate this expression, so differentiation, when we differentiate the equation, d ln of w is constant, so d ln of w will be 0, and we will have d ln of w that is equal to 0, and that will be equal to we will have d ln of n ln n minus differentiation of summation ni ln ni. Okay, now over here also we all know it very well that n are the total number of particles and the total number of the particles in our system is constant. So this particular term will be 0, this particular term will be 0 because the differentiation of constant will be 0. We will be differentiating only this particular term, and hence we will have the also there is a negative sign, so I could multiply the whole expression with negative sign, and this will become a positive sign. So we will have differentiation of summation ni ln ni, and that is equal to 0. We know that this could be differentiated using differentiation by parts, that is, if we have any differentiation, that is differentiation of x into y, then x differentiation of y plus y into differentiation of x. This could be obtained by differentiation by parts. So we will have summation ni constant, then we will have differentiation of ln ni, and that will be 1 upon ni into dni, plus if we keep ln ni constant, summation ln ni constant, then we will have only differentiation of ni will be dni, and that will be equal to 0. So both these terms will be cancelled out, and we will have summation of dni plus summation of ln ni dni, and that is equal to 0. Now this summation of dni is also equal to 0 because we know that we have summation of ni, and that is equal to n, and n are the constant. So when we differentiate both this, we will have differentiation of ni, and that is equal to dn, and that will be equal to 0. Okay, so differentiation, that is summation dni, will be equal to 0, and how this could be equal to 0, I will be showing you in a few minutes only in the later part. For a moment we are considering that this is 0 because dn is constant, and hence this will be 0. So over here this term is also equal to 0. So we are left with summation ln ni dni, and that is equal to 0. So this expression, it represents the most probable distribution. Now this most probable distribution, this is for say n number of particles, that is, we have considered that we have n number of particles and the total energy is E. So over here what we need to do is, this expression for most probable distribution, we need to bind it between the number of particles and total energy. Because for example, as we have discussed this example, suppose if I am putting a second instant stick, or in local language if we say agarbatti over here, then what this person will experience is that the amount of smell is increasing. So amount of smell is increasing, that is, this second instant stick is is giving out us, and the number of particles in the system is are increasing, as well as the number of the number of particles are increasing, as well as the energy of the system is increasing, and as a result now the system will move towards the new maxima. Okay, so in order for the universal, or in order to obtain a universal expression, this expression for the most probable distribution, we need to bind between the total number of particles and the total energy of the system. And in order to do that, we will be using the Lagrange's method for undetermined multipliers. And as a chemist, we don't need to go in detail into this method. Just we need to remember that as we have seen this condition, that is summation dn is equal to summation dni, and that is equal to 0. So this is our equation number 1. The second condition is summation, that is for the total number of energy, we have the total energy, that is E is equal to summation niei, and this we could write it as dE is equal to summation ei dni, and that is also equal to 0, because the total energy of the system is also constant, so the differential will be equal to 0. So this is our equation number 2. So over here we will be multiplying equation number 1 with alpha, equation number 2 with beta, and this is suppose our equation number 3. So we will be adding equation number 1 plus we will be adding equation number 2 plus we will be adding equation number 3. So this is the Lagrange's method, and as all the three are equal to 0, technically their sum will also be equal to 0. So we will be adding all these three expressions, and we will have summation ln ni dni plus alpha into summation dni plus beta into summation ei into dni, and that is equal to 0. Now we can take summation one side and dni other side, so we will be left with summation ln ni plus alpha plus beta ei into dni, and that is equal to 0. Now over here, in order to make this expression equal to 0, either dni should be equal to 0 or all the terms in this bracket should be equal to 0. Now over here dni is not equal to 0. And how dni is not equal to 0? Dni, it literally it means we could write it as dn1, dn2, and so on. How this is not equal to 0? Let me explain. Suppose we have energy level E1, energy level E2, and energy level E3. Now in these three energy levels, suppose total 10 molecules are distributed in this particular manner, that is in energy level E1 we have 5 molecules, in energy level E2 we have 2 molecules, and in energy level E3 we have 3 molecules. Now there is no restriction in filling up of the energy levels, so I could pick up any particle from any energy level, and I could distribute, or I could substitute, or I could throw that particle in any particular energy level without any restriction, until and unless the number of particles are not increasing, as the system is a closed system. So I could take two particles, say from energy level E1, and I will throw it into energy level E2, and I will take one particle in energy from energy level E1, and I will throw it in the energy level E3. So what will be the change? That is, I am taking total 3 particles from out from here. So now new distribution, E1 will have 2 particles, E2 will have 4 particles, and E3 will have also 4 particles. Okay, so when we look at the change, then dn1, there are 3 particles have changed, so this is -3. When we look at the change for dn2, there are 2 particles have increased, so we could write +2, and when we look at n3, then 1 particle has increased, so 1. So when we look at individually dn1, dn2, dn3, they are not equal to 0, but when we take the summation, when we are taking the summation of dni, then -3 plus 2 plus 1, so that is equal to 0. So that we have just what written, that is summation dni is equal to 0. So summation dni will be equal to 0, but when we are looking individually at dn1, dn2, dn3, so that will not be equal to 0. So over here individual dn1, dn2, dn3 is not equal to 0, so hence dni is not equal to 0. So obviously, in order to make this expression equal to 0, the terms which are in the bracket should be equal to 0. So we could write ln of ni plus alpha plus beta ei is equal to 0. Also, one thing I forgot to mention, initially we are considering that the system is a non-degenerate system, and we will introduce the degeneracy in the later part of the derivation. So further we will rearrange this expression in the form ln ni is equal to minus alpha minus beta ei. In few of the foreign authors book, this is taken as minus also, so it depends from book to book, and in order to remove ln, we could make it as ni is equal to e raised to minus alpha into e raised to minus beta ei, and this expression is the celebrated Boltzmann distribution law. This expression is the celebrated Boltzmann distribution law. This expression, it gives the number of particles that are distributed in different energy levels, and alpha and beta are the arbitrary constants, and the value of beta, it is proved it is equal to 1 upon kT, where k is the Boltzmann constant and T is the temperature. So this is the celebrated Boltzmann distribution law. For if we say we know the amount of energy, we could obtain the number of particles in that energy. If we know the number of particles, we could obtain the amount of energy of that particular system. In order to introduce the degeneracy, or we know that energy levels may be subdivided into the energy levels, or there may have different energy levels with almost similar energies. So with energy levels having similar energies, we need to introduce the statistical weight factor, that is statistical weight factor gi into the expression, and hence our expression for degenerate system will become ni into gi e raised to minus alpha into e raised to minus beta ei. Further, we can take summation of this expression, and when we take summation, we will have summation ni, that is equal to n, and that is equal to e raised to minus alpha into summation gi e raised to minus beta ei. This will be the expression. Now suppose this is our equation number 4 and this is our equation number 5, then we could take the ratio of both these expressions, that is equation number 4 divided by equation number 5, and we end up with the expression that is ni upon n is equal to e raised to minus alpha from here, and e raised to minus alpha from the numerator, and e raised to minus alpha from the denominator will be cancelled out, and we are left with e raised to minus beta ei upon, we have gi summation gi e raised to minus beta ei, and this expression is the celebrated Maxwell Boltzmann distribution law, and this expression, it gives the relative population of the particles in different energy levels. Ni are the number of particles in certain energy level, and this gives us the total number of particles. So this ratio, it gives the relative population of the particles in different energy levels, and this is also referred as probability density. Also, with the help of this expression, we could obtain the population of population or relative population of the different energy levels in a particular system. And this term, that is summation gi e raised to minus beta I, this term is referred as the partition function q. I have also prepared a video on partition function, so you can see that. So hopefully the derivation is clear and it was lucidly explained. Thank you very much.